Okay, for this next day of 2.2, I guess you could say it's our fourth day of looking at some derivatives here. This time we're going to see a piecewise function defined at 2x minus 5 if x is less than 1, and x cubed minus 4 if x is greater than or equal to 1. And it says state the domain of the derivative. Now, before you do anything, the big question is, do you think this curve is continuous everywhere? There's one prime location where we should be super concerned. What x value do you think is going to be a potential hot spot for a discontinuity? 1. Well, let's see. We could say, does f of 1 exist? Well, what assignment, A or B, would deal with that? That would have to be B. And you'd say, well, yeah, f of 1 would be 1 cubed minus 4, and 1 to the third is 1, 1 minus 4 is negative 3. You could say, well, continuity says your function must be defined at any x location in question. Would our limit exist, do you think? Well, I think the big question is, does the limit as x approaches 1 from the left exist? Because if it's from the left, we have over here, let's see, plug in a 1. 2 times 1 minus 5 would be negative 3. Oh, would you look at that? Would you look at that? From the right side, you could say we already know what's about to happen. We just plug that into the function. Hey, we've got agreement. The limit as x approaches 1 of this function is equal to negative 3. My left side and my right side are in agreement. Does that mean I have continuity? Well, not until I check number 3. Does my limit equal my function value? Yes. We're continuous at x equals 1. Now, I'm reviewing continuity right now, but that's so important that we do. Because if a function is not continuous at any location, the derivative cannot exist at all. I'm going to say that again. That's so important. If a function is not continuous at any x value, immediately you can say your derivative does not exist. Super important. Well, that being said, even though this is a necessary condition, it's really not sufficient right now to say that our derivative exists. We have to know that our tangent line slope from the left and from the right would be in agreement. Well, tell you what, I think so many of you would say, well, wait a minute. If I took a derivative of just 2x minus 5, what do you think we'd get? Just if I gave you 2x minus 5, what's that derivative? A 2. And kids would be like, oh, that's nice. Yeah, how about if I gave you x cubed minus 4? What would that derivative equal? 3x squared. Very good. And now watch, I'm going to be very careful about putting any equal bar here. Clearly, if x was a lot bigger than 1, we would have a derivative of 3x squared. And clearly, if x was less than 1, we'd just have a derivative of 2. So this is good. It's promising. Do you think we can say that our derivative will always exist, though, right now? It won't. I hope you can see why. Let's think about this. The limit as x approaches 1 from the left of our derivative would be really the limit as x approaches 1 from the left of 2. And what would that tangent line slope have to equal? 2. Then you could say, now wait a minute, what if I approach 1 from the right side? If I'm approaching 1 from the right side, guys, my derivative, we just saw, would be 3x squared. When I plug in a 1, what do we get? 3. Guys, we have a very serious problem here. We have such a serious problem. The left side derivative and the right side derivative disagree. This disagrees. What do we know? We're going to know that f prime of 1 does not exist. F prime of 1 does not exist. So, what's the domain? The domain for f prime is all reals, but x cannot equal a 1. Your derivative is fine no matter what you want to plug in, but don't plug in x equals 1. We have an issue there. By the way, what do you think is happening from what we're seeing? What if we were to graph it, what kind of an occurrence would we have at x equals 1? A corner. Because the left side tangent line slope would be 2. The right side would be very close to it. It would be 3, but they're not the same. We have a corner there. Okay? All right, one more problem, guys. Oh, wow. This is a classic AP question. Next year, you guys will be taking the College Board's big AP exam, a wonderful opportunity to earn university or college credit. And that's magnificent when you can do that. In 1998, there was a huge calc reform. There was such concern because even at Harvard University, this is known as the Harvard Reform. At Harvard University and Ivy League schools, students were going into science labs where you would see table data like this. And the professor would say, well, let's do some calculus on our data. And the students would look at it and say, what are you talking about? I don't have a function. And they said, you don't need to have a formula. You do have a function right here. It's just your data points. Let's do some calculus. And the kids said, I have no idea what you're talking about. And these were some of our brightest young minds in the country. So because of this huge concern in the late 90s, calculus has never been the same ever since. God bless you. We now have a lot of data in tables. And they're saying, would you approximate, if I'm giving you this, the derivative at x equals 4? Now, of course, we won't be able to get the exact answer. But they're saying find a tangent line slope approximation at f prime of 4. Do you know what we're going to do? We use a secant line. We use a secant line to get a pretty good estimate. And the secant line slope is the slope you've been using for years and years and years. y2 minus y1 over x2 minus x1. And, of course, right now, kids will look at this and they'll say, well, that means you need 2 points. Obviously, f of x is represented by y. And kids will understandably ask, well, what 2 points are you going to look at? And the answer is surprising. You could choose a whole bunch. You could come up with 3 different answers. And on the AP exam, they would honor any of those 3. Sometimes kids will say, well, wow, I'm going to pick these 2 points to estimate what's happening at x equals 4. They might say, I'm going to look at 3, 13. I'm going to look at 4, 16. And you could see f prime of 4 would be about y2 minus y1 all over x2 minus x1. Kids will say 16 minus 13 is 3. 3 over 1, you'd say, I think I'd get 3. Hey, great answer. That's one of the answers that they will accept. Someone else will say, now wait a minute, who's to say you're going to choose 3 and 4? Wow, I'd much rather choose something different. I'd much rather choose the 4, 16 and the 5, 17. Say, okay, you can do that. You definitely could do that. What will bother kids is they'll say, wait a minute, you're going to get a different answer. Yes, you will. y2 minus y1 all over x2 minus x1. It looks like you get 1 over 1. It looks like you'd say it's about 1. Kids will be like, wow, that's a bit off. Yeah, that can happen even on the AP exam. Look, there's one final way that we could find a tangent line slope around 4 or approximate it, and that's symmetrical. Working with points around 4. Work with 3, 13 and 5, 17. And surprisingly, we will get 17 minus 13 all over 5 minus 3. Kids will say, well, wow, that's 4 over 2. I get it too. Yep. Any one of these would be valid. Any one of these would be a great approximation for f prime of 4. That being said, we're going to have the same worksheet, guys, that you were working on. It's just that we'll be doing 37 through 47 all, and then also number 55.